Okay, welcome back to the second part of our unit on landscape evolution. We've been talking about how landscapes change over the course of time. And in this part of the unit, I want to say something about equilibrium, which is a really important concept in physical geography, but also a little bit controversial. If you're writing an essay about the plural and contested nature of the discipline, this concept of equilibrium would be a nice example of that. And I've put a paper on the KLE for you to have a look at. It's available online through Keel's library. A paper called Geomorphological Equilibrium, Myth and Metaphor by Bracken and Wainwright, 2006. And they make the point that equilibrium is a central concept in geomorphology. It's a really important idea in our understanding of landscape. But they also explain in that paper how it's often been misused, how it's led geomorphologists astray, and how it's in some ways had a quite damaging impact on the nature of our discipline, because it's led us into, if you like, a false sense of security about our understanding of how landscapes work, whereas in fact equilibrium has some serious issues with it. That isn't necessarily something we're going to get into in huge detail in this module, but certainly as you carry on, if you continue with your physical geography into second and third year, those are the kinds of issues that you might encounter in more detail later on in your module. But for now, just have a look at that paper if you get a chance, and just check out the abstract, just skip through it and get a feel for roughly what it's on about, but don't get bogged down too much in all the detail at this stage. So from what we were talking about in the previous video, you'll get the idea that an equilibrium situation is one where things are holding each other in balance, if you like. So different things are going on in the environment, but as they're going on, there isn't necessarily any massive directional shift in what's happening in the landscape. Things aren't changing majorly. And this example is just a photograph of the Powder River in Wyoming in the States. And you can see there you've got erosion on the outside bank of the channel there on that meander. You've got deposition on the inside bank. The channel width varies a little bit as discharge increases and decreases, but there's a balance maintained because you have erosion in some locations, you have deposition in other locations, the channel shifts a little bit, it shifts a little bit back, and you wouldn't be massively shocked or perturbed by day-to-day changes in that pattern, because there is a long-term equilibrium that's keeping the system working in a kind of predictable way. So channel form is constantly adjusting in response to the process, and there's an interaction between process and form, keeping things in balance. And that's what we tend to think of just intuitively as an equilibrium situation. Now, there are actually lots of different types of equilibrium that we can talk about. Static equilibrium, for example, that term often is used to describe a situation where nothing is changing. If I drew a graph of river width against time, channel width against time as the river discharge fluctuated over the course of time, if channel width wasn't changing, if nothing changed, we'd just have a horizontal flat line. Well, that's static equilibrium. If discharge is varying a little bit, so the river width is increasing, decreasing over the course of time, but over the long run not really going anywhere, it's staying roughly the same, well, that's what we call steady state equilibrium. And that's kind of what I was talking about in that example of the Powder River a second ago. Things are happening, but there's no long-term direction of travel, if you like, in what's happening. It's staying steady. Dynamic equilibrium is when there is a long-term direction of travel in what's happening in the system. So not only do we have the kind of the fluctuations that we in channel width, for example, in my case study here, not only do we have fluctuations over the course of time as we move forward along a steady flat trajectory, we actually have a sloping trajectory. So maybe the channel width is getting steadily wider and wider and wider, a bit wider one day, a bit narrow, a bit wider, a bit narrow, but getting gradually wider. So we have a ziggy-zaggy line, but it's trending in a certain direction. And metastable equilibrium is where we have some sudden change in the system. So we have a stable state, then there's an interruption or a disruption, a disturbance to that state, and so we shift to a new steady state. So it's steady, but with steps or interruptions or variations. Those are just a few examples. You can read up on this in the set reading to get an idea of what the different types of equilibrium are, but just be aware that there are different types of equilibrium, or different ways of describing equilibrium. It's important in particular that you understand metastable equilibrium, because this is a kind of situation that's very common in the physical geography examples that we'll be using in this module. And make sure that you understand those terms: characteristic form, which is kind of the form that you would associate with a particular process environment, with a particular equilibrium. If things are in balance, then this is the form that you will get. Then if you have an impulse for change, a climate change or some earthquake or some change in characteristics that's going to make your landscape respond to it, there'll be a reaction time, there'll be a lag, a pause. When something happens, there's not an immediate response, there's a reaction time. There's then a period of time during which the adjustment is being made. It takes a while for the river to get wider or for the river to get narrower by deposition. Whatever the change that's going to occur, it takes a while for that to happen. That's the relaxation time. And then after that, the river or the landform that you're talking about will reach its new characteristic form, the state it needs to be in to match its new environmental setting. At that point, it's back in equilibrium. So there's a period of disequilibrium after the impulse for change, where, for example, climate changes, until your morphology gets back in sync with that. You're in a period where you're not in equilibrium, so there's a period of disequilibrium. Read up on those terms, so they're explained much more effectively in diagrams in the books, but I'll let you go and have a read of that. Make sure you understand those terms, and you'll see them in action in case studies later on in the module. There's another reading for you here, and I'm going to suggest that after I shut up in a second, you pause the video and have a read of this abstract, and maybe come back and have a look at it later on as well. It's quite an important little bit of text. You can get the whole paper online through Keele Library if you're one of my Keele students. But that abstract, and the paper as a whole, but even just the abstract, explains for you quite clearly what some of the key terms that I've put in your set work to find out about. Some of those key terms are explained quite nicely in that paper. So either pause the video now and have a look at that, or come back to it and have a little look later on. So, some key points that we've made so far. Now I've rattled through some of this and I've maybe skipped over things that you'd like me to have said more about. You can catch me about those maybe in the live session on Friday. But here are some of the key points I hope you've pulled out from what I've been talking about. First of all, landscapes evolve over long time periods. Not evolution in the same sense as biological evolution, but evolve is a term that we use. They change gradually over the course of long time periods. And they do that partly in response to changes in the environment, and partly in response to these equilibrium situations that we've been talking about. Landscapes experience periods of equilibrium where the environment, the processes going on, remember we've talked about process environments before, and the forms are all matched up. You have a characteristic form for the processes that are going on because the processes are in sync with the environment. Everything is in equilibrium. But sometimes, often, landscapes are out of equilibrium with their environment because the environment has changed and the processes are only just beginning to catch up, and so the landforms certainly haven't caught up yet. So the landforms don't necessarily reflect the current environmental conditions. Well, we don't have a characteristic form, we're not in an equilibrium situation. So you need to be aware of things like the response time, and I'm rolling in together there, the reaction time, the delay between the impulse and the reaction to it, and the relaxation time, the time it takes for the landscape to actually make its change. There's a gap before it even starts changing, then there's a period during which it is changing. So there can be a very long, thousands, tens of thousands or hundreds of thousands of years response time. In the UK we're still responding to the change of environment at the end of the last ice age. We're going to talk about that in the next unit. And also be aware of the idea of response thresholds. Sometimes a form cannot be easily recovered. So if you have a major event, a landslide for example, or a big flood affecting a river channel, even when you go back to normal, if the landscape has had a major change and has crossed some threshold of recovery, it can be hard for it to come back from that. Equally, if you increase river power just a little bit, or you change the climate or increase the rainfall rate just a little bit, that might not be enough to make a difference. You increase it a little bit more, still might not be enough. Increase it that little bit more and you cross that threshold and whoosh, suddenly everything starts happening. So that's what I was talking about previously about non-linear responses. It isn't necessarily that a little push leads to a little reaction and a big push leads to a big reaction. It can be the other way around. There can be long gaps, there can be complications, there can be feedbacks. So that's the complexity and the fun of geomorphology. So what I'd like to finish off with is this case study, very quick case study of a non-equilibrium situation. This is one of my favourite field sites where I've worked over many, well, I was going to say many years, but it's many decades. I've been interested in work in this area. It's at the Russell Glacier, which is an outlet glacier of the Greenland ice sheet, just above the Arctic Circle on the west coast of Greenland. And this is the channel of the Meltwater River, which is draining past the Russell Glacier. Now, the channel, most times you go and visit, so I've been to that location, I don't know, maybe 20 times or more, and most times that I've been there, at all sorts of different times of year, the channel seems to be much bigger than necessary for the volume of water that's flowing through it. Why is that? Why is the channel so big, given that there isn't really that much water flowing through it? And you're probably having lots of ideas already. You're saying, well, it looks pretty cold on that day, you've got your hat on. Probably this is in the spring or the autumn, there isn't much meltwater yet. So the river is actually set up to deal with the summer meltwater. And that's a perfectly good hypothesis. You could say, yep, there's big seasonality in the discharge of meltwater in these two photos, one there in the summer when there's lots of water in the background, and one in the winter when there's no water in the background. Temperature there was about -30, the river's frozen over, the lake's frozen over, there's no moving water anywhere around. So maybe the channel is adjusted to the seasonal maximum flow. So how would you deal with that if you were organising your dissertation or organising your research project? How would you test that hypothesis? Would you go and have a look at what the annual maximum flow was like? And believe it or not, this is it. The channel that you're seeing there is, well, as it says, it's about 250 metres across. And you can see the sections that the river is occupying, which isn't actually that much of the channel. And you can see some massive bed forms there. Dunes, ripples, all sorts of things, but at the scale of metres and tens of metres in size, far exceeding anything that you would associate with the amount of water that's going through that channel right there in that photo. And that channel right there in that photo was taken in the middle of summer when you'd expect the discharge to be at a maximum. So why does that river channel have that morphology? It doesn't appear to be matching the river that's flowing through it. So why is that? Well, we discovered why it was when we happened to encounter on one occasion a massive flood going down that river. It was orders of magnitude more water going through the river than normal. We witnessed this flood, and after it we walked upstream to try and see, well, where has all this water come from? Because the flood only lasted a couple of days. Where's this water come from? So we went to have an explore, and as we walked upstream we found this huge delta formed of boulders that you'd need an enormous volume of water to carry, appearing to come out from the edge of the glacier, the edge of the ice sheet. We kept on walking and we found a lake basin. Now this photo was taken on a different occasion when the lake basin was full of water. It's a lake dammed up against the glacier. When we went there immediately after the flood, the lake basin was empty. And this is the explanation for those floods. Just occasionally, water ponded up at the edge of the glacier is catastrophically released into the glacier, through the glacier, out of a tunnel, into the river, and downstream past that channel that we've been talking about. On this map you can see, on this satellite image, you can see on the right hand side a label where that ice dammed lake is, and then the water occasionally drains from that lake into the glacier, emerges where that middle photograph is pointing its arrow, which is where the delta was, and then the water flows off to the left of the picture, past that photo you've seen before. The little circle there is putting a ring around a group of people standing on the sander, on the outwash plain, to give you an idea of scale. But that's where the water subsequently goes past. And those floods happen for a few years and then they stop happening because they depend on things to do with the dynamics of the glacier. And we went back, we saw that first flood in 1984, I think, and then we went back year after year for many years, and we didn't see another flood for for over a decade, and throughout the 1990s the floods weren't really happening. They started happening again later on, but all through the 90s there were none of those big flows. But the river channel retained that large format, if you like, that big scale of channel, despite the fact there was only small amounts of water flowing through it, because it was out of equilibrium with the current environment, but in equilibrium with those occasional massive floods. And it's another example of that kind of threshold response where it's hard for the river to recover from such a big event if all it has afterwards are little events that aren't even touching the sides. The river in non-flood years doesn't even touch the edges of the flood channel, so it doesn't really modify it very much, and it doesn't really recover very much from what happened. So that was just a quick example to illustrate the kind of situation where you might find yourself very easily in a non-equilibrium circumstances. And a nice bit of homework for you to be doing after this session would just be to think about other examples of that. And those of you, if you're doing the patchwork assessment, that would be a really nice thing to try and think of, or try and look for it, even in your local environment or anywhere in your reading. Environments that are not in equilibrium with their current landscapes or landforms that are not in equilibrium with their present process environment, because they're actually in equilibrium with something else that's gone or is coming back later, or they can't recover to their previous form because they've crossed that point of no return, that threshold of recovery. So I've just put the conclusion slide from earlier back up so that you can have a look at that as we're finishing off. And I'll leave you there. I think I've given you plenty of things to think about there, so I'll leave you to think about those, and I'll see you next time.